Okay, so what we've done so far today, kind of reviewed the syllabus a little bit. You know that you got to wrap up exam one before coming to class on Thursday. Everyone's on that same page. Did that example problem, so work it again. You'll know you got it as soon as you're bored. That's when you know you understand it. I do want to get into chapter 3, and then I think right at the end of lecture, I'm going to talk a little bit about the summary, the first summary, because a lot of the concepts in the summary paper are similar to what you'll see in chapter 3. So I'm not going to read the book to you. I am going to just take a look at the figures. The majority of the information is sitting there in the figures. Oh, and while I'm thinking about it, somebody had a question. This comes up a bunch about the reserve to production ratio, and right now I am on page 52. If you don't have your textbook with you, just write this down. I'm on page 52. I'm looking at table 2.3, and one of the questions that comes up is which country is sort of the least sustainable, if you will. And in the second chunk of that table, it says selected countries, and the top 5 are China, the U.S., Russia, India, and Japan. And together, Japan is sort of the lowest in terms of percentage of global population. Russia is second lowest. The U.S., believe it or not, is third lowest at just under 5%. India has 17.5%, and China has almost 20% of the world's population. Now, if you look on the next column, it says how much energy is produced. And again, that's just in a percentage. China produces 18.1%, U.S. 14.8%, Russia 10.3%, India 3.8%, Japan 0.08. 0.8. Sorry, 0.8, yeah, there you go, 0.8%. So not even 1%. And then the next column over shows energy consumed. China consumes 19.5%. It produces 18. So it consumes 19 and produces 18. So it has to import some of its energy, right? Because its usage is 1% greater than its production. The U.S. Produces 14.8 and consumes 19.3. So we also import, at least when this table was written. Also importing. Russia produces 10.3 and uses 5.6. Russia is an exporter. India produces 3.8 and consumes 5.2. India is an importer. Japan, again, 0.8, consumes 4.3. Big time importer. It's consuming 5 times what it makes. So Japan was the answer to that question in terms of the least sustainable. And I don't know. It's funny. I was just in Japan, and we were looking at the rebuilding of the Onagawa power station. It's just north of Fukushima. Can't go near Fukushima still, but they're rebuilding their seawall from 13 meters to 30. Ooh. 100-foot seawall, 800 feet long, 6-foot thick tubular steel.
How deep are they going?
It's a good question. I don't know how I'm guessing the pilings are.
Well, they're going into rock there.
Yeah, they're right there. And they were built. They were still kind of finishing, just putting some very large caulk beads between the pilings, because they're letting these pilings sort of like a big piano, set of piano keys, and letting that thing flex. So
Right.
yeah, something else. But when that tsunami hit, no nukes, and they started importing compressed natural gas in a big way that really brought them back. Okay, so hope that clears up up the question on Chapter 2. So let's look at Chapter 3. And the Chapter 3 is just what do we use energy for? And this is sort of a little bit of a segue into Chapter 4, where we'll really dig a little more into the physics. This is just kind of more looking at historical uses, society uses, sort of, big picture stuff. And also, it gets us talking about the different types of energy. Okay, so there we go, far left, chemical energy, coal. When you see that, what's it mean, chemical energy? What's that mean to you? How can you have chemical energy?
Through a chemical process, it has the potential to release energy.
Yeah, and what chemical is in that coal?
Carbon.
Carbon, yeah, it's number 6 there on the periodic table. 6 protons in its nucleus, 6 electrons. Carbon will bond with just about anything. Carbon is one of the more prolific bonders. So, yeah, what happens? That coal, carbon combines, and we're not going to get into a whole lot of chemistry just now. We'll do a little bit more later. But basically what you're looking at carbon plus oxygen. Gosh, it's just that simple. Carbon plus oxygen becomes CO2. There it is. And what comes off is heat. There are other things in there as well. If there's hydrogen, you'll get some water, etc. We'll get into that later in the course. So that's what we mean by chemical energy. Once that carbon burns with oxygen, chemistry happens, heat is released. Yeah, Kat.
So when there's combustion of any type of element or anything burning, it's just adding oxygen, basically?
More or less, yeah. That's exactly. Any combustion you can think of as a chemical reaction involving oxygen.
Also, that's just combining whatever it is with oxygen.
Yep, exactly.
Okay.
That's exactly right. That's exactly right. And we aren't going to get into the physics of combustion here, but basically what's happening, heat itself and temperature is just molecules moving faster than they otherwise would, and they move fast enough that they collide, and they collide hard enough that they stick. You can just kind of think of it that way. And now you've got a CO2 molecule. And it's not until that CO2 molecule finds itself inside a plant that it gets ripped apart. There are really, to my knowledge, no synthetic ways to destroy or break that molecule. If you've got one, let me know. Tell me secretly up here, and we'll get cracking. But up to now, nature's figured it out. Nature's got a way to say, hey, give me a photon, and I'll rip that CO2 molecule apart, take the carbon to build my plant structure, and off comes these nice little oxygen molecules for the rest of us to breathe. Okay, so that's chemical energy, and we call that primary energy. It's sitting there in the earth. It's ready to use. There are many other forms of primary energy. I think Peter covered those. So, as we mentioned, when that combustion happens, it's turned to thermal energy or heat energy. Again, that's just a lot of molecules smacking around. What's the kinetic energy going on inside the power plant?
Like movement?
Yeah, it's movement. You've got steam moving. That's going to spin a turbine. We've got a turbine sitting right here in the back of the room. That's an air turbine rather than a steam turbine. When that spins, you've got a magnet, makes electricity. You've even got little magnets sitting back here, and as soon as you spin it, magic, presto, out comes electricity. That is sent over wires, goes through the meter on your house. You plug in your lamp, you do your homework. So that's the flow of energy. Now, when you look at this was a big wake-up call for me, if you will, when I first started looking at this stuff in detail. Gosh, how long? Good 12 years ago. All of that energy actually does become heat, and we'll look at that in a little bit. But
Did they
once
use it, or did they just release it?
well, so
steam?
That's a good question, and we'll get into whether that heat is used. Out in Colstrip, I don't think any of that heat is actually used for district heating. It could be, the town of Colstrip is sitting right there, they could, send that heat into their sidewalks, and they wouldn't have to go out and shovel. They could send it, and again, I don't know, maybe it's in there, they could send it out into the community so that each home didn't have to have its own natural gas line to heat water, for example. But in general, yeah, 2/3 of that chemical energy turns into heat at the power station. It's just the second law of thermodynamics. We'll get into that later. But really, at the end of the day, all of it just becomes heat. Disorganized energy that you can't really capture. You might say, well, if I heat the atmosphere a little bit, I'll get some wind that'll come back, and sure, then you put up your wind turbine, et cetera. But ultimately, it all just becomes heat. Okay. And it's useful, and then it's gone. Okay. Now, I really like this slide a lot. It also made me really think about sort of the trajectory of civilization, and maybe later in the course I'll show you this paper by Shramsky that sort of shows, where's the peak? We sort of start out here as a tribe of primates. Well, a few years before that, but maybe 70 to 200,000 years ago, and this sort of baseline of food is relatively constant. You might say, well, maybe we don't have to eat so much anymore because we're not having to keep ourselves warm and all that. But that's how much energy goes into keeping us alive. That's that 2,500 calories per day that we use. And then here all of a sudden comes technology, domestic energy. There's your campfire, right? There's your pile of wood, your campfire, keeping the wolves at bay. Well, Egypt, now we got to build buildings, build chariots, build dams, canals. There's your industry. Transport, China, and again, I don't know exactly what technology. I don't. Does the book talk about whether these guys are using? Is this just wind? Are these just sailboats?
Yeah.
Okay, so I mean that can just be as simple as a sailboat. I stuck up a sailboat, and now I'm not rowing myself around anymore. I've got a technology for transportation. Europe AD. This is expanding as we're keeping ourselves warm. Some of this, I think, at some point, some of this starts to become coal. Industry expands, transport. Here's England. Look at all the industry. This is the booming industrial revolution. Machinery, tractors, etc. And then finally, here come services. And I don't know exactly what this is in England, but now you can just think of this as your computers, your fax machines, yeah.
It's electricity, town gas.
Oh, is that what it is? Oh, okay, there you go. Yeah.
Street lights and stuff like that.
Yeah. Right. So there we go. Keeping the keeping the lights on, keeping the city safe. Same thing. So these are the four main sectors of energy, and almost any energy policy is going to look at that. If you get a chance, I recommend going and reading some Amory Lovins. He will go out and sort of attack each one of these sectors and say this is what each one of these sectors is going to look like in the future when we move away from the fossil fuels and move towards renewables.
What was his name again?
His name is Amory Lovins, AMORYLOVINS. He runs an institute called the Rocky Mountain Institute.
Okay.
And he was sort of a foreseer of a lot of this in the 70s, and people are like, oh, you and Jimmy Carter are crazy. What are you guys talking about? But he has since been awarded multiple doctorate degrees. He's got all kinds of books, and the Pentagon calls him up and says, hey, Amory, how are we going to continue to power our fleet around the world, et cetera. So he's big thinker in this field. Very proud of the fact that he has no furnace or boiler in his house in Aspen. He's built it up big enough. The thermal mass of that house is large enough. There's enough renewables coming in that he doesn't need to burn anything to keep warm.
Wow.
Okay, so these are just some early examples. Here, this is really nothing more than going from kinetic energy or mechanical energy into some other kind of mechanical. You're gonna grind your corn, you're gonna pump your water. You're just moving things around. No electricity. Pretty simple. And this is what's called a windmill. Sometimes you'll see people calling the wind turbines up on the High Line windmills. They're turbines. They make electricity. The windmill is just mechanical to mechanical conversion. Here's another one, and this is something, I look at this and, well, this is what my yard looks like, and this is what my neighbor's yard looks like. And you can sit down and again, do a little word problem on this. Obviously, this chemical energy in that wheat, in that agricultural product, more than likely is going to go into food. You could also imagine taking the chaff, maybe turning it into some fiber. You could turn it into clothing. You could also just you could burn it. It's got chemical energy and turn it into electricity. There's also technology coming online that's going to become popular, very popular here pretty soon, just of pyrolysis, where you would take and heat that in the absence of oxygen, so you're not actually combusting it, and then you're harvesting the carbon. And I think we're going to see a lot of that coming, because carbon has a lot of uses in the steel industry, in water filters, in pharmaceuticals. Japan announced not too long ago that it wants to build a space elevator by the year 2050. Well, cheaper than rockets, maybe safer than rockets. They're going to need a lot of carbon to do that. They're going to need a lot of solid carbon nanotube to do that. So I think we're going to see the carbon industry sort of change fundamentally. The issue here, yeah.
And there's actually, on that very topic, there's a documentary right now, very interesting, on the space elevator.
Oh, really? Okay.
On Netflix.
Yeah.
It's out right now.
Yeah.
Space is a lot closer.
It's pretty cool.
Space is a lot closer. Yeah, it's only 60 miles away, right? Yeah.
They should really build that.
It's the centrifugal force that will keep it up.
Well, but back to this figure. The question is, could that harvester run from the chemical energy in that wheat? Like, could you imagine building a machine to just pull in that wheat chaff and burn it at a rate? I'm thinking you probably could.
Has the energy density to do that?
I don't know. It'd be a good problem, though. I mean, it'd be a good so, because you could look and say, well, it's burning diesel or gasoline or whatever its fuel source is at a certain rate, gallons per minute. You can turn that into horsepower. You can turn that into watts. You could then come through and say, what is the chemical energy in that wheat being harvested? What's the comparable? And then getting into some of the papers, the next question is, well, so that these chemical bonds were formed, just this year. There's just they were photosynthesized within the last few months. The carbon bonds being burned inside the harvester were formed a long time ago. Those were chemical bonds, formed in oil deposits. So I look at this sort of as a time machine almost. You're consuming these very ancient carbon bonds to harvest very, very recently formed ones. So just something to think about. That's what I see when I see that. Okay, talk about time machine. I think this is the hearth, the modern kitchen and warming station back in Victorian England. fairly elaborate. You can see you've got, you can keep yourself warm, you can make yourself tea, you can, heat something up and put that under the bed at night. Here's a skillet over here, there's an oven for baking, all kinds of different ways to poke and play with the fire and try not to burn yourself. This over on the side, I don't know,
Icebox.
so this is the ice box?
Oh, I'm just.
It could be, yeah, it could be. But then you've got your two kettles on top.
Maybe it's just storage for the kettles.
Yeah, but this is sort of at the dawn of electricity, just think about living in a house, pre-electricity. And no, town gas, if you will, and maybe there's, I don't know, this might have even been burning coal. I don't think you would want to cook your food over a coal fire, but, it could also be used to burn coal, so.
On that note, isn't charcoal a form of coal?
Is charcoal a form of coal? Well, charcoal is typically manufactured from wood, whereas coal, you might argue, is wood, but really old wood that's been underground for a long time and mixed with other things. So, yeah, maybe. Okay, and then here, you need hot water to keep your clothes clean. So this is, again, just domestic energy, sort of pre-electricity. You don't have a washer dryer to heat your water and spin your clothes. I think we're going to get kicked. I keep forgetting we don't end right on the hour. So one or two more slides, and we'll wrap it up here. And here's the town gas. I think Tim was mentioning that. You could think of this as a service, something to keep crime rates low. There's still, you'll even see Gaslight Villages. There's one in Grand Rapids, Michigan. There's one up in Vancouver, British Columbia. And this could be, think of as a district lighting
Can you
office.
smell it through the town at all? Or since it's all being burned right away, you can't?
Well, it's a good question. If you had a leak, as you know, methane, which is the primary source, is odorless. You cannot smell methane.
And will they add odors?
Yeah,
lot of gas
that's
to
right,
those.
for safety, absolutely. But, and sometimes, some of this might even have some sulfur in it. If there was sulfur in it, you sure would smell it. Yeah, absolutely. Kind of that rotten egg smell. Here's human power, again, pre-electricity. If you want to run your industry, find eight guys that, and this is about a 1 horsepower machine, right? Each one of these people is running at 100 watts, maybe 200 watts if you're really getting after it. If you're Lance Armstrong, you might make 600 watts, or Usain Bolt.
Back there all by himself.
Yeah. But
You can
early,
make a whole bunch of zeros.
early industry. And here's another kind of obvious example of modern electricity just for transportation. So safety. Okay, well we'll pick this up, and again take a look at the summary. The summary has a lot of very similar concepts. What I try to do in that summary is talk about different energy types, just like we did here in chapter 3. So that'll get you thinking on that. Thanks a lot.
Thank you.
Yeah.